Look at this dashboard simulating a global e-commerce payment backend. The engineering prompt requires this system to process 1 million transactions daily. The instinct is to treat this as a high-throughput scaling problem, requiring heavy sharding and optimized compute. This breakdown shows the reality of that requirement. 1 million transactions divided by the 86,400 seconds in a day yields roughly 11.5 transactions per second. Any standard single-node database can easily process this. Raw speed is a false objective here. In standard web architecture, a dropped packet or a duplicated request is an acceptable margin of error. A user simply refreshes the page. In financial architecture, duplicating a request means charging a customer twice, triggering compliance audits and regulatory fines. A modern payment backend must assume the network will constantly fail. The true engineering challenge is prioritizing state correctness over raw performance. The perimeter of this system begins at the API layer, specifically the standard post v1/payments endpoint. A standard payload enters the perimeter. A single checkout click generates one payment event. If purchasing from multiple sellers, the system splits that event into distinct payment orders. Looking closely at one payment order, the monetary amount field is strictly passed as a string. Storing financial amounts as floats or doubles creates an immediate vulnerability. Different hardware protocols, languages, and serialization methods execute floating point math differently. A clean number like $100.05 can easily fracture into an imprecise decimal as it traverses the network. Over millions of transactions, these microscopic fractional discrepancies slowly accumulate into compounding rounding errors, thoroughly corrupting the financial data. Enforcing strict string data typing at the API boundary eliminates hardware-level interpretation. It is the foundational defense against arithmetic drift across millions of transactions. Storing user payment details introduces the severe compliance burdens of the Payment Card Industry Data Security Standard, or PCI DSS. To bypass this liability entirely, the architecture follows a rigid rule. Internal servers must never touch, process, or store raw credit card numbers. This layout maps the flow across 3 nodes: the client device, our internal backend, and an external payment service provider. The handshake begins when our backend sends a payment registration to the provider, which returns a unique token, or nonce. The backend passes this token to the client, triggering it to render a secure hosted payment widget directly from the provider. When the user enters their credit card, that sensitive data flows directly from the client to the provider. It never touches our servers. By structurally isolating the sensitive data payload via a hosted page, the system successfully initiates the money movement while offloading the highest security risk. Once the provider charges the card, it asynchronously sends a webhook back to our system confirming the payment succeeded. 3 internal components record this event. The payment service coordinates status, the merchant wallet updates balances, and the ledger documents the truth. This ledger table operates on a strict append-only constraint, utilizing double-entry bookkeeping. A $100 debit from the buyer requires a simultaneous $100 credit to the seller. This enforces a zero-sum mathematical property, where every operation resolves to a net sum of 0. Because every fraction of a cent is mathematically offset, the double-entry format provides end-to-end traceability, creating an internal audit trail that cannot be quietly tampered with. Recording a successful charge means updating the wallet, the ledger, and analytics. Doing all 3 at the exact same time introduces a major risk of system failure. This linear chain models the instinctual approach, linking the services together with synchronous HTTP requests. This creates tight coupling. If the analytics server experiences a timeout, it breaks the synchronous chain and fails the entire payment request. Replacing the chain with an asynchronous message queue like Kafka, the wallet, ledger, and analytics services branch off a central event stream. The payment service publishes one payment success event. The queue clones this message, fanning it out to all 3 downstream services simultaneously. If analytics goes offline, the message waits safely in the queue until the service recovers. The wallet and ledger process their updates completely unaffected. Asynchronous decoupling trades immediate synchronous confirmation for failure isolation, allowing the financial state to eventually align without fragile dependencies. Consider the nightmare scenario. A user clicks pay, the network lags, and out of frustration, they click pay a second time. The engineering goal for payment systems is ensuring that request executes exactly once. Exactly once execution requires solving two mathematical halves, guaranteeing at least once delivery while enforcing an at most once limit. To guarantee delivery, transient network errors are routed to a retry queue. The system attempts the charge again using exponential backoff, waiting 1 second, then 2, then 4. Unrecoverable transactions that continuously fail are eventually ejected into a dead letter queue, where engineers investigate the payload manually. But guaranteeing delivery creates a new problem. How do we prevent the system from processing both of the user's clicks, resulting in a double charge? The solution relies on an idempotency key. When the checkout session begins, the client generates a unique UUID and injects it into the HTTP header. This database diagram illustrates how that key enforces the at most once limit. Two identical packets carrying the same UUID approach the storage layer. The first request hits the database, succeeds, and writes the primary key. The second request attempts to write the same UUID. The database's unique key constraint deflects it and simply returns the success status of the first request back to the user. By combining the persistence of the retry queue with the database's strict idempotency, the system mathematically guarantees the user is charged exactly one time, regardless of network chaos. Internal consistency is necessary, but external dependencies will inevitably fail. Webhooks will drop, servers will crash, and eventually the state of the provider and our internal ledger will diverge. This split-screen UI represents asynchronous reconciliation, verifying the internal ledger against the bank's records. At midnight, an automated script diffs both files line by line. Discrepancies are flagged and routed into a manual queue for immediate human investigation. Moving money out of the system to pay sellers simply mirrors this entire architecture, utilizing third-party accounts payable providers to execute the payouts. A robust payment architecture expects and survives failure at every node. By layering idempotency, append-only ledgers, and constant asynchronous reconciliation, the system transforms a fragile web of APIs into a verifiable record of truth.